the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. This video is a continuation of a group of videos on polynomial functions for the pre-calculus student who's about to enter calculus. That's why they're in pre-calculus. What we've discovered so far is how to graph polynomial functions using zeros and multiplicities of zeros. Also, we talked quite a bit about end behavior of polynomials and the shapes of polynomials in general and the shapes of polynomials near to their zeros. So now we graduate beyond that, now that we finished graphing all types of polynomials, and we go into something that doesn't seem totally related, but something called dividing polynomials. Now, part of this you should have seen maybe in your Algebra 1 or Algebra 2 course. It's just long division, essentially. And you'll see that the very first example I'm going to do actually showcases long division. However, as we move forward through this lecture, we're going to get into something called synthetic division, which you can see titled on the screen right here. We have that. So let me actually highlight that. Say this is synthetic division right here. And let me turn that off. And beyond there, we're going to go ahead and talk about a division algorithm and go into more synthetic division and yet again some more synthetic division. And that's pretty much it for this lecture. So if you already know synthetic division, you can kind of skip this. Otherwise, if you need a review of it or if you've never seen it, it's probably one of the coolest ways to do division of polynomials. Now, I should also mention we're dividing polynomials right now because what's going to happen is we're going to actually graph rational functions, which are ratios of polynomials. So we're going to graph beasts like this. And to do that, you need to be able to do synthetic division and long division very quickly. Also, in this very section out of the textbook that I use, we talk about something called the factor and the remainder theorems. And those are critically important, so huge as you move through mathematics that it's important to pay attention to all this. So let's go ahead and dive deep into this right now. Perform this division. Example 3.3, number 1. Perform that division. And to be honest with you, I wanted this example not to do synthetic, but to actually just remind you of how long division happened when you were a Algebra 1 student or something like that. So recall when you did division way back when, if you had like 23 and you were to divide into 1,000, actually let's make it a better number than 1,000. Let's do 2,411, right? You would say, okay, well, 23 as a number does not divide into 2, but it does divide into 24. So let's go ahead and say 23 divides into 24 once. Notice where I place that 1. And then it has a remainder. So to find that remainder, we say, well, 1 times that 23, and then you place that right here. Remember this back, good old from arithmetic, right? And then you would do a subtraction. Oh, 24 minus 23, and you get this little 1. That's the remainder, by the way. And then you would carry down the 1 and the 1, right? And then you'd ask yourself, well, how many times does 23 go into, right? So you continue this conversation over and over again. So this is how we are going to do long division using polynomials. It's a little bit more prescribed with polynomials, to be honest with you. I think a little bit easier. It's a little bit more straightforward. So let's go ahead and repeat that process. We have a 2x being cubed plus x plus 1. Now, I have to apologize beforehand. I just made this example up without checking it. So I don't know how nice or ugly this is going to be. Hopefully it won't be too ugly, but it might be ugly. And that's just something we'll have to deal with. Let's see. So let's go ahead and write down that numerator. It's 6x to the 5th. I like this example because it showcases that if you're missing a power, which we're missing a power of x to the 4th, you'll have to have a little placeholder for it, plus 0x to the 4th. And then we have a minus x cubed, and we have a plus x squared, and a plus, what is that, 2x, and a plus 1. So every single power of x is represented right there. I didn't really need it in the divisor here. I did not need to worry about that, but I do need it in what we would call the dividend here. And so let's go ahead and do this. Just like we did with arithmetic, we'll ask ourselves, how many times does that highlighted piece go into this? I don't really care about the x plus 1. I only care about the lead term of the divisor here. So 2x cubed, it goes into 6x to the 5th. If you need to see the arithmetic behind it, you could say, well, what's 6x to the 5th divided by 2x cubed? And you could easily see that's 3x squared. And so it goes in 3x squared times. Luckily, we're going to be able to check this. But where I'm going to place that is right here in the x squared column. It's not that you have to do this, but this is a good idea. Now let's check our work. We're going to take that 3x squared and we're going to multiply it against the 2x cubed. When you multiply 3x squared by 2x cubed, you get a beautiful 6x to the 5th. But you also have to multiply that 3x squared by the x. And when you do that multiplication, you get a 3x cubed. So let me write that down. Notice where I'm placing that. It's in the x cubed column. And then I'm going to go ahead and grab that 3x squared and multiply it against the 1. And that'll give me a positive 3x squared, which I will place in the x squared column. And now I will go ahead and do subtraction like you would in arithmetic. Now, the beautiful part about being in a classroom is that you get the kind of the feedback from an audience when people sit there and students say, oh, I totally remember this. And, you know, they get all excited. And I'm assuming that's what's happening here, where you look at this and go, oh yeah, I totally remember doing this. So anyway, I go ahead and put parentheses around that just because I need to remind myself I'm actually taking that minus sign, I'm going to distribute it to each of these terms here. And so let's see, 6x to the 5th minus 6x to the 5th. By design, that will always turn into 0. It's a good way of checking your work to make sure you've done things right. And then you have a negative x cubed, and then we're losing, because you're distributing that negative, you're losing another 3x cubed. And so you have a negative 4x cubed. And then you have an x squared, and you're losing 3x squared, so you're at a negative 2x squared. You could bring down everything else if you wish. You don't have to actually, but you can. And now we just repeat the process we just did. So what we're going to do is, instead of taking this 2x cubed and seeing how many times it goes into 6x to the 5th, we're going to take that 2x cubed and ask ourselves, how many times does it go into negative 4x cubed? Actually, for making this up on the fly, this is not too bad. I'm looking at this. So we're asking, how many times does 2x cubed go into that negative 4x cubed? I'll write that off to the side here in green. So let's see, I have a negative 4x cubed, and I'm going to be dividing it by 2x cubed because I want to know how many times it goes in. That'll be a negative 2 times. It's actually a very nice, clean number. So I will write that in the top here, which, by the way, is called the quotient. And I will go ahead and write that negative 2 there. You'll get to check your work to see if you just did things correctly, because you're going to take that negative 2 and you're going to multiply it to each of these 3 terms. Don't worry, those lines I will erase so they won't be in our way forever. But let's take that negative 2 and multiply it by the 2x cubed. You will get a beautiful negative 4x cubed. Remember, we are going to be subtracting whatever numbers we write here. So negative 4x cubed plus a 4x cubed, those will disappear or cancel each other out by design. And so that means that we've done the right mathematics so far. Now we take the negative 2 and we multiply it against the x. That becomes a negative 2x. I'll write that here, negative 2x. And we'll take that negative 2 and multiply it by the positive 1. We'll get a negative 2. And now we'll go ahead, I can erase that blue, and subtract all those bottom values from that polynomial there. So we have a negative 4x cubed plus a 4x cubed. That becomes 0 by design. We have a negative 2x squared, losing nothing. So it's just a negative 2x squared. We have a 2x minus a negative 2x, which is a positive 4x. And then we have 1 minus a negative 2, or plus 3. Now notice, this 2x cubed, maybe I should erase my blue highlighting here, by the way. Oops. Well, I did more than erase my blue highlighting. Sorry about that. Notice that the 2x cubed does not go into an x squared nicely, right? There's not enough power in x squared to support division by x cubed. So this is done. What you see here is a polynomial remainder. In fact, let me circle that up, and I will call this the remainder. Off to the side here. If you don't know why, it is because, again, 2x cubed, maybe I should say it this way, because negative 2x squared, if you were to try to divide 2x cubed into that, the 2's will cancel fine. But this ends up being a fraction involving x, and that's not what we want. We only want polynomials after division. And so this is a no-go. So we can just erase all those, get those out of the way, and now refocus on what we're doing. What does this mean in terms of the fraction that we had up above? Well, it means that if you had done long division, which we did, we would get this 3x squared minus 2, which is again called the quotient, and then we'd have some remainder over some divisor. Now, before I write that down, I want to just showcase why that's true. So if you took, like, I don't know, 2 dividing into 13, let me write that a little bit better. 2 dividing into 13. Well, 2 does not divide into 1, but 2 divides into 13 6 times. Multiply 6 times 2, you get 12. Do the subtraction. 1 cancels 1. 3 subtracting 2 is 1. And 2 does not go into 1 cleanly, so we'd call that the remainder. And when you are in arithmetic, depending on if you're raised in the US or not, there's a specific way you'd write this, but we won't bother because we can say that the dividend over the divisor, 13 divided by 2, is going to be the quotient, 6, plus the remainder of 1 over the divisor. 6 plus a half, or 6 and a half. And that should make sense to you. So when you do this with polynomials, just like the 3x squared just like the 6 ended up being this kind of whole number out front, which is what we call the quotient, the 3x squared minus 2 ends up being that whole number, if you will, out front, again called the quotient, plus the remainder, which we've defined or have found out is a negative 2x squared plus 4x plus 3 over the original divisor. And remember, the original divisor is this guy right here. So it's over 2x cubed plus x plus 1. And so this is how you would do long division way back in the day. Now, a couple things I want to draw your attention to. First of all, you can kind of redevelop this algorithm. This is called the division algorithm. You can redevelop this just by looking at arithmetic. You can, if you ever forget, you can just say, well, what's 13 divided by 2? And so you could do that arithmetic and you get that whatever's here is called the quotient, and whatever you can't divide into at the end is called the remainder, and this is called divisor. In fact, you know what? Rather than circling those up, I'll highlight them, and then on top of that, I will label them. So again, this right here traditionally is called the divisor. This right here is called the quotient. It's kind of the result of your division, the whole numbered result of your division. That I've already, let me highlight this. This piece I've already told you is the remainder. And then the piece in the middle there, I'll use blue for that, the 13. That is called the dividend. Not a lot of people remember that, but that is true. It's the dividend. All right. And likewise, if you look at our pieces here, you can kind of draw the same statements. And there you go. I've kind of labeled them in that picture as well. So this is the division algorithm. And another thing I want to point out to you is that the remainder is always less power than the divisor. If there was the same or greater power in that remainder, so let's say that that power ended up being a 5, let's say, then you could still do long division. You can continue with long division. So what ends up happening is that it's always going to be the fact that the remainder will have less power with polynomials than the divisor. And you can kind of see why, again, because if you have more power left there, if that was a 12th power or something like that, well, the divisor could still divide in. You could use long division to still divide into that. Now, everything I've said here is actually captured in the next theorem. And this theorem is called the division algorithm. And the division algorithm just says that if you have a couple polynomials and you're dividing one by the other, so the numerator, again, is called the dividend. In fact, let me label all those. There we go. So P and D are polynomials. P is just called the dividend. D, being dividing into that, is called divisor. D cannot be 0, obviously, because you're dividing by 0 if that's the case. Then it is true that there exist unique polynomials, one called the quotient and one called the remainder, where the remainder, this guy right here at the very end, whoops, that was my hand that did that. That guy at the very end is either 0, because it could be that D divides evenly and perfectly into P. If that's the case, you just don't have a remainder. That's like saying 2 divides into 12 6 times with a 0 remainder, right? So it is possible that you could have no remainder. Or if it is not 0, it's going to be a polynomial of degree less than the degree of the divisor. And we saw that in the previous example. In the previous example, when we did the long division, the numerator, or the remainder, had less degree than the divisor. And that's what this is just formally stating. And so you get this algorithm. P divided by D is just some polynomial, which we call the quotient, plus a remainder divided by the divisor. And by the way, you will find in textbooks that this is often written as P of x equals D of x times Q of x plus R of x, which is a mouthful. All that basically says is they multiply both sides by D. Right? If you multiply both sides by D, that's what you get. At this level, you should be able to do that. All right. So that's the division algorithm. There's nothing else on this page that I want to talk about. Now I really want to get into showcasing synthetic division. Now I do want to give you a little bit of heads up on how I'm going to showcase synthetic division. When I used to teach this in an Algebra 2 class, I would actually prove synthetic division. Let me tell you, that's not the thing you want to do. I did that as a rookie mistake when I was new to teaching and I was fresh out of grad school and I was super excited, and I still am super excited about mathematics. But the reality is that the juice is not worth the squeeze. you do so much work trying to prove the synthetic division algorithm that you spend like a day on it. And still, students at the end are kind of like questioning what they just saw. So it's much better to say, you know what? Here's mechanically how it works. So forgive me if I don't actually prove synthetic division, but rather justify it and give you a guideline on how to use it. So here we are. Find the quotient and the remainder using synthetic division. That just means divide. Find the quotient and remainder by dividing. Now I'm going to do it actually using long division first, and that way we can verify that our mathematics is correct. We could also sort of build synthetic division based on showing or observing what happens when we do long division. So let's go ahead and do this. Again, I'm doing long division first just to showcase the algorithm. You will really want to pay attention to both the long division and then definitely synthetic division. My calculus students love synthetic division. They're like, oh, I just did it the other day. And they were just like, man, I totally love this algorithm. They totally remember it from this course, so that's good. So we'll start, and I'm going to use a highlighter here, and I'll say, how many times does that x go into 2x cubed? Well, that's a pretty easy division. 2x cubed divided by x is just 2x squared. So we're going to go ahead and say it goes in 2, except I'm not going to use a highlighter to write. It goes in 2x squared times. Luckily, we can check that work. 2x squared times x is a 2x cubed. And a 2x squared times a negative 2 is a negative 4x squared. And then remember, you subtract all these statements, right? And so 2x cubed minus 2x cubed, well, those disappear by design. Negative 5x squared plus 4x squared is a negative x squared, and I'll bring down the 3x and the 7 because I can and I have to. And then you ask yourself, okay, how many times does x go into negative x squared? Well, negative x squared divided by x is a negative x, so that's not too bad. Multiply back through, negative x times x is a negative x squared. Negative x times negative 2 is a positive 2x. And again, remember, you're subtracting that entire statement right there. Negative x squared minus a negative x squared, they cancel by design, so you know your mathematics is correct. 3x minus 2x, well, that's a pretty little x plus 7. The question is, does x divide into x? Nicely, and yes it does. It goes in one time. So I'll put a little plus 1 here. So our dividend is now set. Sorry, our quotient. That's what I meant to say. Our quotient is now set. It's 2x squared minus x plus 1. That's our quotient. Let me go ahead and double check our mathematics by multiplying. 1 times x is x, and 1 times a negative 2 is a negative 2. And again, you subtract that statement. X minus x cancels. 7 minus a negative 2 is a positive 9. X does not go into 9, so this must be our remainder. And I'll highlight that in almost a red here. And I will write in red that that is the remainder. And so if somebody asked, which they kind of are in this situation, find the quotient and the remainder, well, the quotient is that. That's the quotient. And the remainder is 9. Remember what that means. It means that this division ends up being the quotient, which is 2x squared minus x plus 1, plus the remainder over the divisor. So that's what that fraction actually turns into. Now, synthetic division. Now that we know kind of what the quotient should look like and what the remainder is, let's introduce a new method. So if you're going to use something called synthetic division, I just want to make a note here that when you're dividing by x minus 2, You're really saying that if x minus 2 is a factor, well, we know this from a previous theorem that we were introduced to. If x minus 2 is a factor, then x equals 2 is called a 0 for your polynomial. And so what the synthetic division does is it takes whatever will turn this into 0, and you'll write that right here, 2. So let me write this down formally. So synthetic division, if I give you a polynomial divided by a linear factor, and what's critical about this is a linear factor with a coefficient of 1 on the x. That's kind of important for this division algorithm to work properly here, for synthetic division to work. So let's see, we're given a polynomial divided by 1x plus or minus a number. Okay, but I specifically write it as minus c because I want to showcase something. And the polynomial, it looks terrible, but this is just saying it's some nth degree polynomial. So in this case right here, our polynomial is third degree, right? 2x cubed minus 5x squared and so on and so forth. But here I'm just keeping it general. What if it's 27th degree or something like that? The a sub n's, a sub n minus 1s, those are just coefficients for each of those powers of x. So that might be 10x to the 27th plus 8x to the 26th plus so on and so forth down the line until you get to plus 3x minus 1 or something like that. Okay. So what you're going to do is you're going to write this little, almost like a row of a spreadsheet where you have just a separator here, and you write c, which is actually what would turn this into 0. C turns the linear factor into 0. And I should pause, just because you don't need to watch my handwriting the entire time. So that c is positive there because, well, positive c minus c is 0. So that's what turns that linear factor into 0. Anyhow, you write that as the first element in this row, bracket it off so it's separated, so visually it's just separated, that's all. And then you write the coefficients of your polynomial. And by the way, these coefficients, if your polynomial has some missing powers, like our first example did, where I think the x to the 4th term was missing, you need zeros, you need placeholders. And I have written that off to the side there so that you know. All right. Now the next thing, actually let's not do the next thing. Let's go ahead and start with that and see what happens. So I'm going to zoom out here and I'm just going to keep my eye on the original problem, not my work that I did with long division, because what this is going to do is speed up long division in the long run. So I'm going to look at that and say, okay, well, it's x minus 2. So what he said in class was to write 2 with a little kind of a bracket off thing. And then I'll look at that numerator and I'll list out all of the coefficients in descending power order. So it was 2 that's on the x cubed. And let's see, a -5 on the x squared and a 3 on the x to the first. And then the constant was a 7. Again, if any of those, if there was a power of x that got skipped, let's say the x squared wasn't there, I would put a 0 in its place. I need a placeholder. Now, the next thing you're going to do, you're going to skip a line and draw, kind of like what we did here. In fact, exactly like we did there. You're going to draw a line, but instead of subtraction, we're going to use addition. And the reason why you do addition is because you're already taking into account the opposite of that number. You don't need to know this, but that's exactly why it becomes an addition problem versus a subtraction. It's because you're dealing with the opposite of that. So that's why we just do addition. Plus, addition is much easier than subtraction. And in our little method there, I already wrote the little bar with a plus sign. And now we're going to just carry down the first element. So I'm just going to go ahead and write this out. I'm going to do this. I'll go down here, point an arrow. This will be a sub n. So off to the bottom here, I'll just say carry down that first number. So far it's not too bad. You're just listing things out. There's no mathematics involved yet. The only mathematics actually you do is what is the opposite, what basically turns this off. That's the only mathematics that you do so far. Now comes the mathematics. You're going to take this value of c here, and just like in our long division, you would take this and multiply. You're going to do the same thing here. You're going to take this value c and multiply it against a sub n, and you're going to write it right there. I'll write this as c a sub n. And then you're going to add. And then you do the same thing, c times whatever this number is. And you're going to put it here, and you're going to add. Rinse and repeat. You just keep going and going and going. Now, that's the best way for me to write it. I'm sure there's actually better ways for me to write it, but that's the way I'm going to write it right now. So let's go ahead and see how this looks here. The synthetic division says, hey, you know what you need to do? You need to take that 2 and just write it down there. Let me use black here. Actually, I'll use blue as the result. Now, take that, I should use green as the result. Take the number here and multiply it. 2 times 2, well, that will be 4. And you're going to add those two numbers. -5 plus 4 is a -1. Now you're going to just do the same thing. Take that 2, multiply it by a -1, write it right here. 2 times a -1, well, that's a -2. Add them up. 3 plus a -2 is a 1. Now you're going to take that 2. I mean, this is just a rinse and repeat thing, right? Take that 2, multiply it against that 1, and write it right here. 2 times 1 is 1. Add, 2 times 1 is 2. Somebody's probably saying, what just happened to math? Hold on. 2 times 1 is 2. Add 7 to 2, and you get this beautiful 9. And you think, great, you just told me like how to multiply and add things. What do I care about that? Well, here's what you care about that. The answer is supposed to be 2x squared minus 1x plus 1. It has a remainder of 9. 2, -1, 1 with a 9. And what do we have here? Yep, that's right. It's just a faster way of doing long division. It only works if you have a linear divisor, so an x plus or minus number. Also, it really only works well if that linear divisor has a coefficient of 1, but you can actually work it if it doesn't have a coefficient of 1. We'll do an example of that. But here we go. So if this is not 0 at the end, non-zero, that implies that you have a remainder, a non-zero remainder. If your end value is 0, then your remainder is 0. The other things you need to note, the original polynomial, the original dividend, had a power of 2. When you do division by power of 1 on x, sorry, I said 2, I meant 3, because I already did the math in my head. All right, so the original dividend had a power of 3. Power of 3. The divisor had a power of 1. So when I do that long division, or synthetic division, doesn't matter what it is, the quotient should be power of 2. 3 minus 1 is 2. So that's where this 2 comes from, is the fact that you have a power 3 polynomial, or a degree 3 polynomial, divided by a degree 1 polynomial will be a degree 2 polynomial. Well, why am I saying that? Because this is the coefficient of x, not to the third, but to the second. It reduced the power by 1. So now we know that the fraction 2x cubed minus 5x squared plus 3x plus 7 divided by a linear factor of x minus 2, it will end up being a 2x squared minus 1x to the first plus 1 plus the remainder of 9 over the original divisor, x minus 2. And remember, the problem asks what's the quotient and remainder. Quotient is the polynomial 2x squared minus x plus 1. Remainder is 9. Now, I find that synthetic division is so important that I just want to do one more example before we do kind of an interesting sub-example. So let's just make up an example. You could do this yourself as well. If you're going to make up an example, go ahead and just make up any degree polynomial you want for the numerator. You don't have to go nuts here. You could just say like, let's say a 2x to the 7th minus x to the 5th plus x to the 4th plus x to the 3rd plus x squared plus x plus 1. I said don't go nuts in there. Look what I did. And let's divide that by x plus 3. Now, a little bit of fair warning. I just made this up, so it could be terrible. But that doesn't matter. What I'm going to do to use synthetic division, the fact that it is a linear divisor, that tells me I can use synthetic division. I do want to mention before I continue though, you can actually do synthetic division even if the divisor is non-linear, but it requires you to factor your divisor into linear factors and divide by each of those. So that's more advanced. Don't worry about it for right now. You're just learning synthetic division. So I'm just giving you a heads up that in the long run, you can actually sort of use synthetic division for almost any polynomial. But let's go ahead and go forward here. I'll build my little row like the Excel row I said before. You make this little brackety piece just to kind of tell the world that to the right of this will be my coefficients of my dividend, and to the left of this will be that whatever makes my divisor 0. And -3 will make the divisor 0. There we go. And my coefficients of my polynomial in the dividend are 2 on the x to the 7th, a 0 on x to the 6th, a -1, a 1. I should have had you try this to begin with, sorry. You can always pause and go ahead and try the rest of this. Now we continue on. So we had the 2 on the x to the 7th, the 0 on the x to the 6th, -1 on x to the 5th, 1 on x to the 4th, then 1x cubed, 1x squared, 1x, and then the constant. Now, if you were to do long division, this is a lot of work, right? But when you're doing synthetic division, it's as quick as saying, bring down that 2. -3 times 2 is a -6. So add 0 to -6 and you'll get, well, a -6. -3 times, so this is going to grow by accident because I just made this up. -3 times -6 is positive 18. 18 minus 1 is 17. -3 times 17 is a -31, 51. Yeah, I'm going to stop switching. Well, no, I'll switch inks. -51. 1 minus 51, that's going to be a -50. -3 times a -50 is a positive 150. And here's where it really does get ugly, right? Positive 150 plus 1 is a 151. And now -3 times 151, that's -300, -450, -453. You can hear me doing mathematics, by the way, in the background, right? I just do mathematics in my head like that, right? -3 times 100 is -300. -3 times 50 is another 150, so it's a -450. And then lose another 3 on top of that, so -453. Add 1 back, you're at -452. And here's where it really gets bad. So that's negative times negative is positive. You have 1200, an additional 150, so it's 1350 plus 6 is 1356. Somebody, if a mathematician's watching this, they're like, oh, you made a terrible choice for that that constant there. I did. It could have been a 1, but oh well, such is life. I will stick with it. 1356 plus 1 is 1357. Luckily, we don't have much more to go through, just a minor little multiplication. The answer will be negative, I totally know that, right? And 3 times 1,000 is negative 3,000. I'm actually going to write that down. Let's see, 3 times 300 is 900. 3 times 550, sorry, is 150. And 3 times 7 is 21. And so this is the math I would be doing in my head. See, that's 1704. 1704. Yeah, it's not terrible. Okay, it is terrible. Let's erase that out of my head. Finally, add those two up. 4,071 with the negative on it. Add back 1, you're at 4,070. All right, so it looks pretty terrible. Totally get it. But because that ending is non-zero, we have a remainder, a non-zero remainder. And so the, let's see, the quotient is going to be, now we started with x to the 7th. We're going to lose 1 power because we divided by a linear term. So this is going to be 2 x to the 6th minus 6 x to the 5th plus 17 x to the 4th minus 50 x to the 3rd plus 151 x squared minus 452 x plus 1,357. That's the quotient. And the remainder, well, we already know what the remainder is. The remainder is negative 4,070. Now, you could write it that way. That's totally fine. And that's exactly what the answer should be. Or you could have said this entire polynomial here, rational function, if you did that long division, or if you did that division, you would get the following. Let me erase this. And I'll say this is therefore equal to that polynomial, the quotient, that is, plus the remainder over the divisor. And yes, you could always remove that negative in front of that fraction. It's totally fine. But that's how it's done. Notice, had you done long division on something like that, it would have been long. It was already terrible because the numbers I chose, I made it up. However, that's how that's done. It's not actually terrible. Think about how quickly you get to an answer. And by the way, there's something fantastically interesting that's going to happen within 1 or 2 videos from now using synthetic division. So paying close attention to how this is done is critical. So the final problem in this video is just going to be one more, hey, let's do synthetic division. But this time, the linear factor downstairs does not have a coefficient of 1 for its lead term. So what do? You pre-work the problem is my strong suggestion. You rewrite this as 4x cubed. Actually, let me scoot that over if you don't mind. 4x cubed minus 8x squared plus 5 all over, and you factor off of this a 2. That is, you divide off of that linear factor, 2. You'll be left with x plus 1/2. Now, when you do this problem, it is critical to note that you need to re-multiply that 1/2 back through when you get to your final answer. We'll see that in the end. So let me just start by doing this, and then the problem itself will work out nicely. So let's go ahead and do that. So again, you need that coefficient of the linear factor to be 1. And so we force that by dividing off its coefficient. Now I will go ahead and do synthetic division. Now, if you had been following my advice the entire time concerning synthetic division, I had said, whatever that linear factor is, you just want to turn it off. You want it to be 0. And you will find out here that what turns that into 0 is actually negative 1/2. So if you were to start with that without factoring off the 2 here, you would still get the same synthetic division algorithm. It would seem as though everything's working right had you not divided off the 2. But there is a little caveat here, so let me go ahead and just start the division or synthetic division algorithm. We have a 4 as a coefficient on the x cubed. We have a negative 8 on the x squared. We have no x's. and then finally a 5 as a constant. Bring down that 4. I'm not going to use different inks this time. Negative 1/2 times 4 is a negative 2. Add negative 8 to negative 2, you get a negative 10. But a negative 1/2 of negative 10 is a positive 5. Add those two together, 5. Negative 1/2 of 5 is negative 5/2, and that will be a 5/2. All right. So this tells me that it looks as though, I should say, our quotient is 4x squared, because the original power is x cubed. It looks like our quotient is going to be 4x squared minus 10x plus 5. In that we have a remainder of 5/2. That's what it looks like. However, it's actually not true. Don't get me wrong, it's close, but close is only good in, what is it, horseshoes and hand grenades? Like, it's not good enough. And the reason why is because we have that 1/2 hanging out front of this synthetic division we just performed. If you had done it here, you wouldn't even know that there was actually a 2 hanging out in front of that coefficient. So this will be 1/2 times 4x squared minus 10x plus 5 plus the remainder of 5/2 over the divisor of x plus 1/2. Now, if you multiply that 1/2 through, you'll get the following: 2x squared minus 5x plus 5/2 plus 5/2 divided by 2x plus 1. So really the quotient in this case is 2x squared minus 5x plus 5/2, not 4x squared minus 10x plus 5, but half of that. And the reason why is because we had that 2 as a coefficient here. So be very careful. When you have that 2 as a coefficient, or a non-unit coefficient on your linear divisor, factor it off. It's just very safe. Just do this. Factor it off. Do long division on this business here, or synthetic division on that business there. Okay. And once you're done with that synthetic division, rewrite the problem. Just say, okay, so the answer is 1/2, because you had that 1/2 hanging out in front, times what you think is your quotient plus your remainder over your divisor. When you distribute that 1/2 through, you'll take 1/2 of all of those coefficients, and then the 2 itself, when you get to this guy right here, the 2 will just distribute across the denominator there to get you back to 2x plus 1. So your remainder is actually correct, but your quotient was not. So there you go. The final answer is this piece right here. Oops, that is not what I wanted to do. Your final answer is this big old highlighted piece right here. Quotient, remainder, divisor. Now, if you need a secondary example, you can make any example you want up. I said that was going to be the last one, but I just feel like it's nice to see a few examples. So let's just do one last one super quick, and I won't make this terrible, or I hope I won't, right? So let's just say that you have the fraction. Make up any numbers you want, but don't make it too crazy. So I'll just do 3x squared plus x plus 2. Now, something like this, you can actually do, 3, 1, 2. I have to avoid certain numbers here. So 3x squared plus x plus 2. This one you can actually do using long division very quickly, but let's just pretend as though you don't want to. Let's say it's 5x minus 4. Let's just say it's like that. Yeah, okay, so this is going to be pretty bad, but that's okay. I'm all right with that. So when you do this, and that fraction bar is too long, it's bothering me. I'm going to start by saying that's 1/5 of 3x squared plus x plus 2, all divided by x minus 4/5. And now I'll do synthetic division with 4/5. So I have 4 over 5. And my coefficients, 3, 1, and 2. So it can't be too bad, right? Bring down the 3. 3 times 4/5 is, what is that, 12/5? 12/5 plus 5/5 is 17/5. 17/5 times 4/5. And I can make a terrible problem out of any given problem. The denominator is going to be 25. The numerator will be 40 plus another 28, so 68. 25ths. I guess I can make a terrible problem out of anything, right? 2 plus that fraction. 2 is the same thing as 50 over 25ths. Over 25, sorry. Add those up, you get 118 25ths. All right. Actually, it wasn't too bad. Okay. So what this is saying is that this division is going to be 1/5 times. Remember, we had a square originally. You're dividing out a single power. So it's going to be a 3x plus 17 over 5 plus the remainder over the divisor, which is x minus 4/5. Distribute the 1/5 through to see what your actual quotient is. So distributing 1/5 through, you get 3/5 x plus 17 25ths. That's our actual quotient. And then plus 118 over 25 being divided by 5x minus 4. And that is remainder over divisor. There you go. And again, I'm pretty good at making terrible examples, but that is still showcases the mechanics of it. Now, some people will also mention the fact that that is this piece right back here, let me highlight it, is a complex fraction or a compound fraction. Yes, it is. You should probably multiply top and bottom by 25 to really make it nice, because that's just terrible to write it that way. So it might be nicer to say this is 3/5 x plus 17 over 25 plus 118 over, and I'll just write it this way, 25 times the quantity 5x minus 4. It just looks gnarly when you have a fraction within a fraction, so it's much better to write it like that. But that's it. All right, I hope that's at least somewhat of a gentle introduction to synthetic division. Again, this is going to be an incredibly important skill as you move forward in any pre-calculus course, and in calculus and differential equations. Very important in those courses as well.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.